Let's dive right into this explainer. Today, we're going to analytically break down exactly why nature's geometries and its physics completely outsmart standard human engineering. For decades, industrial design has tried to force the natural world into neat little boxes and grids. We've just kind of assumed that simple, linear shapes are the absolute most efficient way to manage land, water, and entire ecosystems. But as we're about to see by looking at the hard math and the physics of natural patterns, well, that assumption is incredibly flawed. We're going to look closely at the mechanics of landscape design to uncover the brilliant geometric efficiency that's basically been hiding in plain sight.
Think about it for a second. When you look at a river, a coastline, a mountain range, or even the cellular structures inside your own body, you almost never see a perfectly straight line. We really have to ask ourselves, why does nature completely abhor a straight line? As designers and engineers, we are so accustomed to drawing straight lines, right? Mostly because they look clean and orderly on a piece of paper. But nature doesn't care about our paper. Nature cares about surface area. It cares about thermodynamic exchange and biological productivity. To understand how we can design smarter, far more resilient systems, we need to really activate our critical thinking here and analyze the mathematical inefficiencies of our industrial straight lines, especially when compared to the complex patterns nature actually relies on.
To really grasp this, we first need to define a foundational concept, the edge effect, or what ecologists call an ecotone. In ecological design, a boundary isn't just a static border or a fence line separating two areas. It's actually a dynamic, highly productive transition zone where two distinct ecosystems meet, like the edge between a forest and a meadow, or land and water. The research shows that forest-meadow edges actually support 15 to 40% higher species richness than the interior of either habitat. These edges are basically complex ecological engines that naturally maximize the exchange of energy, moisture, and organisms.
Section 1. The straight line fallacy.
When we ignore that edge effect and just draw straight lines across a landscape, we are literally leaving yield, efficiency, and ecological health right on the table. This brings us to a brilliant core philosophy from permaculture co-originator David Holmgren: design from patterns to details. What he established is that we absolutely must understand the macrogeometries of nature, so how climate, topography, and water flow actually behave, long before we start plotting specific details like where to place a garden bed or a fence. If we understand the overarching patterns that govern physical space, we can engineer our designs to work with the physics of the environment rather than constantly fighting against them.
To see the real-world impact of moving away from straight-line segregation, just look at this number, 1.2 to 1.5. This represents the land equivalent ratio, or LER. When we study multi-crop systems, like an integrated maize and bean system, the LER consistently hits between 1.2 and 1.5. So what does that math actually mean for us? It means that integrated, naturally patterned polycultures output a staggering 20 to 50% more yield than segregated straight-line monocultures, all on the exact same footprint. By abandoning the straight-line fallacy, we fundamentally increase our total output simply by changing the spatial relationship between elements.
Section 2. Mathematics of the edge. So let's see how we apply this to two-dimensional space. We know that edges are highly productive, right? So how do we mathematically maximize them without having to buy more land? Consider the mathematical contrast between two different pond shapes. A standard straight pond boundary, like a simple circle or rectangle, gives you the absolute minimum surface interface, which creates a highly limited edge habitat. But what if we use a lobular or crenellided boundary? That means giving it wavy, square, or sinuous indentations. If you take a standard 11.3 meter circular pond, it gives you a water surface of 100 square meters. By simply undulating or crenellating the edge of that exact same pond, you literally double its effective circumference. You massively increase the earth-water interface, providing twice the edge space to squeeze in productive plants and diverse habitats. It's basically a mathematical cheat code for productivity, all without changing the total footprint of the pond.
Section 3. Optimizing crenellated boundaries. Okay, so what happens when we pull those wavy geometries up into the air? Let's shift from 2 dimensions into 3-dimensional space and analyze the physics of vertical patterns. The crucial point here is this number, a 20% physical gain. Imagine you have a flat, 2-square-meter garden bed. If you build a central soil mound to a height of just half a meter and wrap a stone retaining wall around it in a spiral shape, you transform that flat bed into a 3-dimensional cone-like herb spiral. Just by moving into the vertical axis, your planting surface area jumps to approximately 2.4 square meters. We mathematically gain a 20% physical increase in productive surface area over the exact same geographic footprint.
But the true genius of the 3D herb spiral goes way beyond just gaining surface area. Let's break down how the thermodynamics and gravity-driven hydrology here create 4 completely distinct microclimates in one single structure. We're engineering these niches using simple gravity to do all the heavy lifting for us. First, the sun-facing aspect acts as a thermal mass. The stone absorbs solar radiation by day and releases it at night, absolutely ideal for heat-loving Mediterranean herbs. Conversely, the shade-facing aspect is completely shielded from direct sun, which naturally generates a cool, damp microclimate for more delicate plants. Then you have the apical or top zone. That's subject to rapid gravity drainage, keeping the soil perfectly dry and aerated. And finally, gravity pulls all that runoff down to the basal or bottom zone, which acts as a sink, creating a wet, high-moisture environment. It's just brilliant design.
Section 4. Aerodynamics of zigzag windbreaks.
Let's step away from the ground space for a moment and analyze the invisible aerodynamic forces moving across a landscape. Just as water and light interact with shapes, wind forces are heavily dictated by the physical patterns they encounter. Contrast a standard straight fence with a zigzag windbreak. A straight fence acts as a solid, inflexible barrier. When extreme winds hit it, the blunt force has literally nowhere to go, making it highly vulnerable to structural collapse. However, a zigzag windbreak utilizes geometric friction. By folding the structure, it drastically increases its structural resistance. It doesn't just stubbornly stand there taking the hit, it actively deflects and diffuses wind forces across a wider area, massively reducing the mechanical stress on any single point. And here is where the aerodynamics get beautifully counterintuitive. The ideal windbreak is actually not a solid wall at all. You might think you want to stop the wind completely, right? But an effective windbreak actually needs to be permeable. It needs to let 40 to 70% of the wind pass right through it. Why? Well, because if you block the wind completely, it creates a massive pressure differential. That results in a violent, turbulent wind overturn on the leeward or downwind side. And that turbulence can severely damage crops and structures. The physics here rely entirely on slowing the wind down via geometric friction, diffusing its energy rather than trying to completely stop it.
Section 5. Topographical microclimate traps. Now, in harsh, arid climates, changing the shape of the ground is a matter of sheer survival. When resources are incredibly scarce, designers use pitted surfaces, kind of resembling a waffle iron, to mathematically hack the environment and capture resources. Let's walk through the mechanical process of how this actively builds a microclimate out of basically nothing. First, the wind sweeps across the barren landscape, carrying airborne organic debris, tiny amounts of moisture, and seeds. Next, the waffle iron pit breeds localized geometric resistance. This causes the wind to slow down and form a small eddy. And because the wind slows, it drops its payload. Materials and moisture fall and are physically trapped in this little microbasin. Finally, all these accumulated materials begin to compose and hold water, establishing a self-sustaining, localized microclimate that allows a plant to survive where it otherwise would have completely dried out. Section 6. Scaling geometric patterns. So at this point, you might be wondering, can we build a waffle iron pit or a giant herb spiral out of a 100-acre farm? The short answer is, we have to adapt. Highly complex geometries, things like tight, intricate mandalas, keyhole beds, and vertical herb spirals, they are perfectly suited for small-scale zones, like your immediate backyard, where manual maintenance is easy. But at the broad-acre scale, these tight geometries completely conflict with mechanical realities. Tractors and harvesting equipment would literally get stuck in the math, and nobody wants to have to explain that to a farmer. Consequently, broad-scale farm designs must simplify these edges into sweeping, keyline curves. This balances the immense ecological benefits of undulating edges with the necessary operational efficiency of actually working a massive piece of land. We've seen the data, whether it's doubling the edge of a pond, boosting surface area by 20% with a spiral, or manipulating aerodynamics by letting 70% of the wind pass right through a barrier. The physics are incredibly clear. Nature's complexity is not random, it is calculated optimization. So if nature engineers its greatest efficiencies through curves, crenellations, and friction, what straight lines in your own design thinking, or even your own life, are secretly wasting energy? Think about that the next time you map out a project. Thank you so much for joining me on this explainer, and I hope this leaves you eager to view the world through a much more dynamic lens.